Hey everyone, this is Christian back with another webinar on the chemical industry this time. I'm going to go through a little about what happens when we transform feedstocks into chemicals. As always, I represent Hulteberg Chemistry Engineering. We specialize in heterogeneous catalysis. We work all the way from research through development into upscaling and small volume production, and we assist anybody from idea to implementation. We'll start with a brief introduction, give you a quick historical overview. There will be then a walk through the feedstocks, see which feedstocks are we using in the chemical industry. Then there will be some more specifics like industrial factors, actors, players, things like that. And then at the end, I will go through the major processes. So looking at production of inorganic chemicals, organic chemicals, and finally something about fine chemicals. I will then conclude the webinar after that. So historically, there's been a lot of chemistry. It's ranging way back in history. We've done very different things using chemistry, but there hasn't been much of a chemical industry until the Industrial Revolution, which started in the mid-18th century. We saw the advent of the steam engine, the automated spinning systems made production more common or more intense. We saw much more textile output, and this increased production increased the demand of chemicals, and it sort of gave birth to the chemical industry when everybody wanted more hygiene products, wanted to use more soap, wanted to also use and produce more textiles and bleach for that and everything. But what is the chemical industry? Well, first of all, we use the chemical and allied industries as a general term. The allied industries are matter transforming industries, but they're not making chemical reactions per se. They're making mixtures like soap and glass. They're included, but the ferrous metal industries are actually excluded. So iron and steel is not included in chemical industries. However, some other metals like titanium and aluminum are included because they're made in a certain way through electrolysis, which means that they are classified as chemical production. Sodium, other alkaline earth, and rare earth metals are also included in the chemical family, so to speak. So they're included in the chemical industry. Normally, the industry has been divided into 4 pillars: alkalis, acids, fertilizers, and dyes, where alkalis and acids were the first ones to come, and as well as dyes and then fertilizers. And you see that at least 3 out of the 4 are relevant for textile and textile industries, which are the first things that came on market. And then in the 1950s, there was a 5th pillar added, and that was the petrochemicals. In the world, the chemical industry is about 2 to 3% of the world gross domestic product. It's about 15% of all manufacturing in the EU, and there's a slight growth on the market, so about 4% annual growth in the chemical industry. It pretty much follows the growth in population. And we divide the chemical industry in different segments. We talk about commodities, which are single pure chemical substances that are produced in dedicated plant, normally at very high volumes and at low prices, and they find themselves in many applications, and we sell them on specifications. So they are sold on what they are, and the same goes for fine chemicals, but fine chemicals, they're also single pure chemical substances, but they're produced in smaller multi-purpose plants, which means that there are several chemicals produced at the same site. The volumes are much lower, less than 1,000 metric tons per year, and normally much higher priced as well. and they find their way into fewer applications. Specialties, on the other hand, are normally formulated mixtures that are not sold on volume or in applications. They're sold on performance. So instead of being sold on a specification, so what they are, they're sold on what they can do. So you sell a surfactant, for instance, based on its performance, not on its chemical content. The chemical industry has a few feedstocks where we can see that oil, making up 76%, is the major one. Then we have gas, coal, and also renewable resources coming into the industry. And if you break it down and you look at coal, it's a rather complex structured molecule. It has a rather high carbon to hydrogen ratio. It contains sulfur, nitrogen, and other minerals, and it can be quite moist, and it's the oldest feedstock used in the chemical industry. The main use is, of course, for heat and power generation, but it's also used for metallurgic operations, and you find it in gasification for making syngas to make ammonia and methanol, as well as the side product, coal tar. When you make coal into coke, you get coal tar, and that's a very common source of benzene, toluene, and xylene and other aromatics. For instance, the best feedstock for carbon black is coal tar based. So coal is still an old feedstock, and it's still used, but not as much as the next one, which is oil. Crude oil consists of different types of hydrocarbons like alkanes, cycloalkanes, aromatics, polyaromatics, and we have nitrogen, oxygen, and sulfur present, and compared to carbon or coal, they're present in low levels. And they're also contaminated by metals and minerals. Vanadium is quite common. The most commonly traded commodity in the world. We covered a lot of this in the previous webinar on oil refining. The good thing about oil is its high energy density and its ease of transportation. But we find these also different contaminants. So we have sulfur, we have nitrogen compounds, we have the metals, vanadium, nickel, and also other oxygenates as well. So they need to be removed before we can process it further. With respect to natural gas, it's a rather varying composition, but the bulk of natural gas is methane, 50 to 95%, but we also see molecules in the C2 to C4 range and some amount of C5, but C5 is and above means that it has rather low dew points. CO2 is also present in the crude natural gas, and before it's output on the natural gas grids, it's usually removed the CO2, but also sulfur content, and it's ironically also added more sulfur via odorization. The composition varies quite a lot depending on geography, and methane is the thing that we want in natural gas. That is why it's normally referred to as natural gas. And we find natural gas use in heat and power generation, but in chemistry it's the syngas processes, making hydrogen, ammonia, methanol in large quantities, but also making reducing gas like CO hydrogen mixtures for making carboxylic acids and so on. If you take a look at the chemical industry from a very high up perspective, we have our starting points to the left. So we have petroleum, we have natural gas, and we also have oxygen, nitrogen, and sulfur. That's sort of the four major inputs, as well as the coal, but it's not in this picture. Then what happens is that these starting products, the feedstocks, are turned into a few commodity chemicals. We're talking about benzene, xylene, toluene, butanes, but also ethylene, and syngas and sulfuric acid. And these intermediates are then turned into a few secondary commodity chemicals like styrene, phenols, isobutylene, butadiene, ethylene oxide, etc., methanol, ammonia. And then we start seeing a lot of intermediates, and at the other end of the spectrum we have all of the consumer goods that we see around us, everything that we use in daily life. And of course, moving from left over here to right, we have a significant decrease in the market. So the market for ethylene, for instance, is much smaller than, or much larger than the applications of polyethylene at the end. So the further right in this picture, the smaller the market, but also the more complex the molecules and the more pricey, of course. And what fascinates me is that when you transform these feedstocks into chemicals, you see all of these small orange dots here. They actually represent catalysts in the transformation, and we can safely say that more than 90% of everything that we see around us in our homes have been in contact with a catalyst on its production. So catalysts are really omnipresent in the chemical industry. We normally say that the important intermediates are ethylene, propylene, butadiene, benzene, toluene, xylene, methanol, as well as synthesis gas, ammonia, sulfuric acid, and chlorine. And they are then transformed into all different other chemicals. But if we start to look at the chemical industry, it's a really diverse industry with several sectors. We talk about bulk chemicals, which is the starting point for most chemicals. Then we have specialty chemicals, agrochemicals, pharmaceuticals, and biotechnology. And I will focus this discussion on bulk chemicals. And if you look at bulk chemicals, we see that it's characterized, this segment is characterized by stability. We also see a lot of consolidation. So there are fewer and fewer players, and they're buying assets from each other and growing. And another important factor in the production of bulk chemicals is economies of scale. I think this is rather telling if you plot the development of the ammonia plant production capacity in tons per day, that we in the 50s were at about 200-300 tons per day. In the 60s, that grows quickly to 700, and it continues to grow in the 70s and the 2000s. And today we have plants installed that are between 3.5 and 4,500 tons per day. And you know that the industry really is dependent on economies of scale when the largest plants are called super mega plants and not just mega plants. Looking at who is active in the chemical industry, we have a number of actors. So we have inventors, ideators, we have owners of process product concepts, we have researchers and developers, we have some consultants, we have engineering, procurement, construction firms, we have component suppliers and process users. To give you a little more flesh, the inventor is someone, a person or an organization that has a new idea, an original idea or concept. And the idea is usually ending up with some kind of company who we then call the owner of the process or the product concept. And they own and control the patents. They have know-how in the area. And we usually call these players the licensor because they tend to license the technology to others, or indeed specialized engineering firms. Both of these actors will most likely receive a license fee for any production. So they're being paid by the ones that use the technology. The researchers, they're the ones that work either at the specialized engineering firms or at the chemical production companies to bring these ideas to market. Make sure that we have enough information to do scale up and build and design new plants. And they're also responsible for enabling this new technology. And the consultants, they fulfill the same role as in any market. They can be technical or market, and they're responsible for small parts of the development chain, or in certain parts of the construction, or indeed looking at marketing and market aspects. Engineering, procurement, construction, or EPC, they perform the engineering. They do front-end engineering and design, but they also do component specification, they do purchasing, and they do assembly and construction. And these tasks are either done at the EPC company or by just using subcontractors. But either way, the EPC is ultimately responsible for the result. And finally, you have component suppliers, and they provide equipment like compressors, heat exchangers, etc. And they're based on the specifications of the EPC. The EPC, based on their front-end engineering and design, have a number of component sheets that they need to buy stuff to. And these component sheets are matched towards the inventory or the product catalogs of the equipment providers. And if there's a match, you will get a quote and you buy. Otherwise, you have to make something that is tailor-made, which also happens. Finally, at the end of this long list, we have the process users, which is the ones that we normally think about as chemical companies, and they own and operate the final production plant. So they actually make the chemicals, and they make sure that they have a safe operation, that they have a good split between feedstock and final chemicals. And it's actually quite interesting that the companies that we think of as chemical companies sometimes even outsource operation and are then only to be considered logistics companies. Then the question is always, is it really this simple? Absolutely not, because there's a lot of cross-linked relationships. There are many companies doing multiple roles. There are specialized engineering firms that also have production of specialty chemicals in the form of heterogeneous catalysts, for instance. And some companies have their own engineering departments and they build their own plants. So it's not that simple, but this gives you at least an idea of the framework moving forward. All right, so that was the industry at large. I will now see if I can break down the current production processes to you in a good way. So we'll start by talking about inorganic chemicals, and the largest inorganic chemical is sulfuric acid. It's actually the largest chemical in general, both organic and inorganic. Then we'll talk about ammonia, and from ammonia you can also make urea and nitric acid, and we'll cover the chloralkaline process, a very unfortunate process in its development. We then turn to organic chemicals. We talk about steam cracking for making ethylene propylene and how you transform that into polymers. We'll make a quick stop in producing methanol, and then from methanol to formaldehyde. Finally, a little about fine chemicals. Sulfuric acid, it's, as I said, the largest product in the chemical industry, about 200 million tons per year. Historically, there's been a very close connection between a country's sulfuric acid production and its gross domestic product, but that's no longer true in our international globalized world. A majority, 60% or more, is used for making fertilizers, mainly for producing phosphoric acid. So sulfuric acid is mainly used for making other acids, and we produce it from elemental sulfur. It used to be mined, but nowadays it's mainly from refinery byproducts. The other option is to make it when you make ore, like copper ores contain high sulfur content, you get sulfuric acid as a side product, and we also in recent years started seeing people transforming SO2 from chimneys into sulfuric acid as a combined environmental control measure, as well as a way to produce sulfuric acid. But if you look at the traditional process, we start with a liquid sulfur, which is molten, and we burn it with oxygen into SO2. Then we react it with more oxygen to SO3, and then absorb it in water. And the first primary reaction here is just traditional oxidation, while this one here is a catalytic unit operation, which has some kind of thermodynamic restraint to it. So to be able to oxidize SO2 into SO3, we have to be at low temperatures. So this is the temperature in Kelvin, and we want to use an excess of oxygen. And for doing this, we normally employ a vanadium pentoxide catalyst, and it's rather advanced process and reactor design with intercooling. I'll come back to that. And if you look at the equilibrium, you normally do this in a multi-step process where you have the reactants coming in, you do a catalytic step, you get your temperature increase, then you cool it down, another catalytic step, cool down, another catalytic step, and cool down, and then a final catalytic step. And then you get this behavior compared to the equilibrium curve. So you do reaction, get closer, cool down, get closer, and then you end up with a concentration at about 98.5. But if you magnify, you can actually get away from the equilibrium curve if you do an intermediate absorption of SO2. So you remove some of the reactants or products actually between the third and fourth bed, and then you can get as high as 99.7, 99.8% conversion instead. This looks something like this, that we start bringing in our sulfur and our air in our top left here. The air is actually first contacted with the concentrated sulfuric acid that comes out, and that absorbs all the moisture in the air, and then the air and the sulfur is reacted at high temperatures, above 1000 degrees C. It's then cooled down, and we do this reaction and cooling, reaction, cooling, and then reaction. And at this final reaction step, we extract the gas, we do cooling, and then more cooling and condensing, and we do absorption with sulfuric acid, and then we remove much of the SO3 that has been formed, and then we bring the temperature back up, and we do the final reaction step. Then we take and we condense the effluents, and we absorb it in another absorber to get rid of the SO3, which is now almost fully converted. The rest is sent to a stack, but the sulfuric acid here is then mixed with some water, and we put it in storage tanks, and we then finally can output it as concentrated sulfuric acid at about 98 to 99%. Synthesis gas, or syngas, is another very interesting intermediate. It consists of carbon monoxide, hydrogen, and some CO2, and it's produced from carbon-containing material, most commonly natural gas, but we also see it from naphtha, so a little heavier hydrocarbons, liquid, or coal via gasification. The needed or desired relationship between CO and hydrogen depends quite strongly on the application. So if we want to make hydrogen, for instance, for refinery hydrotreating or hydrocracking, then of course we want 0 CO. But if we want to make substitute natural gas, we want our 1:3 ratio. If we want to make alkenes, 1:2, methanol, that's the same ratio. For making aldehydes, the oxo reaction, it's a 1:1. And for making carboxylic acids, we want to have as much CO as possible. Then we also have an interesting relationship, which is the nitrogen to hydrogen ratio, which should be 1:3 for ammonia synthesis. And it's called synthesis gas for a reason. Now, this is a figure from one of my PhD students' thesis, Paltuno, and he started to just draw up the synthesis gas here. And from it, you can make pure hydrogen, or you can make ammonia. You can make mixed alcohols. You can make substitute or synthetic natural gas. You can make methanol. Methanol can then be turned into dimethyl ether, which can be used as a diesel fuel. Methanol can be turned also into olefins or gasoline. And you can use the syngas in a Fischer-Tropsch reaction to make olefins or waxes and paraffins that can then go into diesel fuels or gasoline fuels, or indeed chemical production. So the reason why it's called synthesis gas is, of course, that it's possible to synthesize so many different things from it. And the size of the arrows here sort of represent the current use compared to future uses. The most common way to produce the syngas is steam reforming. It's when we take natural gas and we react it with steam. It's an endothermic reaction, so we need to add heat to make it go towards equilibrium. It forms hydrogen, carbon monoxide, and carbon dioxide. And there are all these interconnected reactions. And one important concept is the steam to carbon ratio, which should be above 1.8 at least, to avoid solid carbon formation on the catalyst. So here are the reactions. You take methane, you react it with hydrogen into CO and more hydrogen. And the CO is on forward reacted with more water to form CO2 and even more hydrogen. And in parallel, you also will have some reactions with methane and CO2, which is called dry reforming, because you do it without the steam. And in that case, you also form CO and hydrogen. The side reactions that we see is disproportionation of methane, forming solid carbon and hydrogen, as well as the boudoir reaction, where 2 CO is combined into solid carbon and CO2. These are undesired side reactions, leaving solid carbon on the catalyst. The process is done in a multi-tubular reactor. We have about 500 to 600 tubes, which are 7 to 12 meters in length and somewhere between 70 and 130 millimeter in diameter. And the catalyst is packed inside, and this catalyst has to be rather stress resistant. When we pack the catalyst, the reactors will be cold. Then we heat the reactors to somewhere between 800 and 900 degrees, which means that the metal will increase in diameter and the catalyst bed will pack. And then when we turn the furnace off, the tubes will shrink. So if the catalyst isn't strong enough, you will see a significant formation of fines, which increase pressure drop and do bad things to your catalyst bed either way. The furnace is usually fueled with either the natural gas or some off gas from purification. And of course, you need rather nice steel alloys to handle the combination of pressure, temperature, and reducing environment. Catalysts are normally nickel-based, so 15% nickel. We add traces of alkaline or noble metals to avoid solid carbon formation. The supports are thermally stable, like alpha alumina, magnesia alumina spinel. They're really sensitive to sulfur, so we need to reduce sulfur content down to the ppb level. And there's this startup shutdown issue that I told you about with the hot-cold reactors. And of course, we have to work with a significant excess of steam to avoid solid carbon formation. The next thing that can happen is that if our aim is to produce ammonia, is that we do something that is called a secondary reforming. When we leave the primary reformer, we exit at about 750 degrees. We will have a small amount of methane still in the gas due to equilibrium. We do this at about 30 bar, so there's going to be some methane left in the gas. So we can then add air. Air is added to a reformer bed, and then we have another catalyst which helps us to increase and react, first of all, the oxygen with hydrogen to increase the temperature to about 1250, and then the methane will also convert. So we'll go to very low methane levels. But since we're introducing air, we will actually also get our nitrogen to hydrogen ratio correct for ammonia synthesis already there. What we also need to do is to maximize our yield of hydrogen. And we do that using another equilibrium reaction, which is called the water gas shift, where we take carbon monoxide and react it with with water to form carbon dioxide and hydrogen. And the purpose is to increase the hydrogen to CO ratio and also enable removal of the carbon oxides, because CO2 is much easier to remove than the CO. It's mildly exothermic and it's also equilibrium controlled, but it doesn't depend on pressure that much, or actually at all. And you get to about 3,000 to 7,000 ppm at the exit of the reactor. So it's still some CO in the gas, but it's not that much anymore, mainly CO2. We do it due to the equilibrium in several steps, and we call the first one high temperature water gas shift, and the second one low temperature water gas shift, where the high temperature one uses iron chromium catalyst, or indeed there's been a new zinc oxide based catalyst that has come to market in recent years, which is of course free of chromium, which is a very good thing. There's also a low temperature shift, which traditionally uses copper zinc catalysts. And these reactors operate adiabatically. So for high temperature shift, we go in at about 350, 360 centigrades, while for the low temperature shift, we can enter the reactor at about 230 degrees. And if you plot it versus equilibrium, we go in, we have about 15% CO by volume. We do reaction, we increase temperature to about 500 degrees, the outlet step of the high temperature water gas shift. We cool down to the 230 degrees. We do another low temperature step, and we do another conversion of the CO, and we end up with 3,000 to 5,000 ppm of CO. We need to remove the CO2. So acid gases has to come out, but there is also an option, and that is mainly when we work with high sulfur containing solid feedstocks, that we have carbon disulfide, carbonyl sulfide, and H2S formed. And in that case, we first of all need to react the sulfur containing molecules into H2S, and the H2S is then removed using some kind of scrubbing technique together with the CO2. It can be an MDEA or MEA scrubber to get rid of the acid gases. But if our target is to produce pure hydrogen, we normally use what we call a pressure swing adsorber, which uses the difference in gas-solid interaction between the different gas components. So the hydrogen will pass straight through these columns, and CO2 will pore condense, and CO will be retained on kinetics. So you will get a nice separation without doing scrubbing if your ambition is to produce pure hydrogen. All right, so that was syngas production. One of the main output chemicals from syngas is ammonia. It's one of the most used chemicals in the world. It consumes about 1 to 2% of the world energy, and it's really the cornerstone in the modern agriculture due to the nitrogen part in all industrial fertilizers that we use. So ammonia, we can use it to do urea. We can make it into ammonium nitrate, ammonium phosphate, and ammonium sulfate. All of these are, of course, fertilizer components, but we also see it going into nitric acid, hydrogen cyanide, acrylonitrile, and other molecules that we can use. Yeah, here's the MEA that we use for the acid scrubbing. So ammonia is quite interesting and highly relevant, and it's produced at really high pressure, so somewhere between 125 and 300 bar pressure, and at medium temperatures, so 430 to 500 degrees. And again, we have an equilibrium restricted exothermic reaction, like so many others in this bulk chemical field. Sulfuric acid, water gas shift, etc. Methanol as well. But here we take and we combine nitrogen with hydrogen into ammonia. And as you can see, the reaction is favored by high pressure and low temperature. And we find some kinetical practical limitations at about 400 degrees. We do this again in a multi-stage reactor with intercooling. We can do either direct quenching or we can do indirect cooling. And historically, gasification of coal has been the main feedstock, but modern processes are really based on natural gas, and there's a really good energy integration. So here you can see the equilibrium curves at different isobars, and you can see that industrial plants today work somewhere in this region here, and the energy consumption has really come down. And today, if the theoretical level, which is required just looking at the chemical reaction and its endothermicity, is 21 gigajoules per ton, modern plants are somewhere in the 24, 25 range. So very good energy integration in these plants. The reactor is normally intercooled. So we have, again, 3 stages in this case, but catalyst with cooling, more catalyst, and then cooling, and finally some more catalyst. And we get the same zigzag behavior with respect to temperature. So preheating, we heat up over the reactor, we cool down, heat up, cool down, and heat up again, and then the final cool down. And this is a heat exchanger section in the bottom. And we approach equilibrium curve, but we try to work somewhere around the maximum rate curve. But here you can see something quite interesting, that even if we have high conversions in the reactor and we work along the maximum rate curve, we actually do not expect to be much higher than 20% coming out of the reactor. So that makes us do certain things on the process level. And if you look at the process, this includes both the syngas part. So we take steam, natural gas in the bottom. First, we need to we preheat the natural gas. We remove the sulfur compounds that are used for odorizing the natural gas. We add steam and we add some CO2. CO2 can be used as a small substitute to the steam to adjust the ratio between CO and hydrogen, mainly for methanol. We preheat it. We enter the reactor side at about 500 degrees and 30 bar, and we do reaction in the radiation section. So we burn a lot of gas here with oxygen, and we heat these tubes on the outside. And the exit temperature is somewhere at 750 degrees here. Then we take the syngas, we go to a secondary reformer where we add also air to do this reaction, where we bring the temperature to 1250 and get the right nitrogen level in the gas. We make some high pressure steam, we cool it down, we go through 2 steps of shifting, high temperature and low temperature shift, coming out here with almost only CO2, hydrogen and nitrogen in the gas. Methane is low, CO is low. We go through the CO2 removal. So we cool it down and we allow the gas to be contacted with an amine solution, which reacts chemically with CO2. The CO2 is stripped off in a stripper and released. The gas here will contain a large amount of hydrogen, a large amount of nitrogen, as well as the few ppm of CO that we still have left. So it's the 3000 ppm minus whatever sticks physisorbs here in the CO2 removal. But the CO is actually a very strong catalyst poison. So to avoid having the ammonia catalyst poisoned over here, we put a methanator in between, which takes the CO and uses some of the hydrogen to actually form some methane here, just to avoid catalyst deactivation. Then we go through, we remove some of the steam that has been formed just in case, and then we go from 30 bar into the 125 to 300 bar range here. And we mix the fresh syngas coming from the purification process with a recycle, and the recycle is also syngas which has passed through the reactor, and the ammonia that has been produced is removed, of course. So we take the mixture, we compress it, we preheat it, we make sure that we get rid of more ammonia. So when we increase the pressure, we will actually get more ammonia condensation. So this is actually cooling to get the ammonia out. We then take the syngas, go into a preheater, and we go into the top of the reactor. We do reaction, and to cool down, we actually inject more syngas, nitrogen, hydrogen mixture in between. So reaction, cool down, reaction, cool down, reaction, cool down. Now we have a stream coming out with a high, well, at least 20% ammonia content. We cool it down in 2 stages. We condense the ammonia. We do that in 2 stages, and we get our ammonia product here. We get some purges here, and we do extract about 5 to 10% of the syngas to avoid accumulation of low content species in the gas. One of the products that you can make with ammonia is urea when you react the ammonia with CO2. And this is, of course, the first example of any organic compound synthesized from organic material. So you have first a reaction where you form this ionic complex. And then so this is a carbamate. And then you do a slower reaction, which is the decomposition of this carbamate. This is an uncatalyzed equilibrium reaction, so it's actually not something that uses a catalyst, and it's limited by practical operating conditions. It's done in the liquid phase, and we have these 2 stages. First, the formation of urea, and then the decomposition of the carbamate. So that also translates into the process. So you take liquid ammonia, and you take CO2, and interestingly enough, this CO2 can be the CO2 that we remove from the gas from the previous section. So when we make the ammonia, the CO2 that we form in the syngas production is actually a good match volumetrically to the ammonia that we use for urea production. We go into a reactor at 180 degrees and 140 bar just to keep everything liquid. Then we do this quick reaction, forming the carbamate. Then we go into columns, first at high pressure for decomposing the carbamate. And we do lose some ammonia here. We go then to a lower pressure. We will have even more ammonia and CO2 lost. But here in the bottom part, we will have urea, and it's sent to finishing, which can be tableting or prilling or whatnot. And this nitrogen, ammonia, CO2 is of course recycled back to the start. Another thing that we do from ammonia is nitric acid. It's about 55 million tons, so it's one of the top 15 commodity chemicals. The nitric acid is normally reacted with more ammonia to form ammonium nitrate, but it's also used to make explosives like ammonium nitrate fuel oil mixtures, ANFO. And the reaction is quite straightforward. Just like in the production of sulfuric acid, it's an oxidation reaction. So we do ammonia oxidation. We try to only form NO and NO2, and then you absorb the NO2 in water to form the nitric acid. Yeah, and this is the overall reaction. So ammonia plus 2 oxygen molecules forms ammonium nitrate or nitric acid as well as water. But it's really important that we try to limit the conversion, because this is not an equilibrium restraint reaction, but the final position of this reaction is, of course, that we combust ammonia into just nitrogen and water, and we don't want to do that. So to do that, we try to just limit the reaction time and use a selective catalyst, and it's actually a very expensive catalyst because it's an alloy of platinum and rhodium that is in a wire mesh form, and we use very, very short residence time. We're talking 0.1 to 1 millisecond, and in industry there are two processes in use, single and dual pressure, and the reaction is strongly exothermic. So if you look at the process, it takes the ammonia in the liquid state, we vaporize it, we mix it with air, which is pressurized, and we go into the reactor at about 80 degrees at 4 to 5 bar, and we do the reaction, very quick reaction over the catalyst, so 0.1 to 1 millisecond residence time. We cool down and we produce steam using the exothermic heat. We continue to make steam outside. We cool down further, then we condense it in a final stage. We take the liquid part, enter into the column, we take the gaseous part, and we also compress it here. So this is an example of the dual pressure process, where we have a lower pressure in the reactor and a higher pressure in the column. A single pressure reactor uses the same pressure in both stages. And we add water. We also need to cool because the absorption reaction is exothermic. We strip off some entrained NO, NO2, and then we get our nitric acid product in the bottom. We then take the air that has been used in the process and we send it through a vent, and we use actually an expander here to drive the compressor. For the dual pressure process, the absorption of NO, NO2 in the absorber is high enough to be able to avoid having a NOx purification on the vent here. But if you use a single pressure process with a lower pressure, you would actually have to also do NOx cleaning here. Chloride is the final bulk chemical, inorganic, that I will go through. It's the 6th most produced chemical worldwide. We produce it through electrolysis of aqueous sodium chloride, so normal table salt. It can also be produced through the electrolysis of hydrochloric acid. But in a vast majority is made from the sodium chloride and natural deposits, or indeed sea salt. And there are 3 electrolysis processes. And as I said, there's been some bad luck in developing this process. The first technology that was developed was based on mercury, which has a significant and known environmental drawback. So there was an alternative developed, which is called the diaphragm process, which uses a membrane made of asbestos, which was, of course, then found out to be not very good to lungs and things. And finally, today we use a membrane process, and it's what we need to do to keep up with the changes in environmental and human control. The overall reaction is the same for all of them, and we see that we react the table salt with water to form sodium hydroxide as well as hydrogen and chlorine gas. There is an advantage to using the mercury cell because it has a very high sodium hydroxide solution concentration even without vaporization. But of course, the disadvantage is that it requires higher cell voltage, so it consumes more electric energy. It has to have a much purer brine, so much purer salt solution. And of course, the stringent mercury contamination will put this out of business. And indeed, in the EU, there is a phase-out process which should be completed this year. The diaphragm cell, on the other hand, uses much less pure brine, which is advantageous. It uses lower voltage than the mercury cell, so it uses less energy. However, the sodium hydroxide will be contaminated by sodium chloride and much lower in concentration. The chlorine will contain some oxygen, and then of course the asbestos is a problem. So this is only, again, a phase-out technology, and you're allowed to renovate but not build new plants based on this technology in the EU. Membrane cells, they have a very pure sodium hydroxide coming out. They use 33% lower energy than the mercury process. And of course, a big advantage is that they have no mercury or asbestos in the process. However, the sodium hydroxide concentration is quite low, so maximum 33%. There's oxygen in the chlorine gas, and there's also a very high purity brine requirement. But still, this is the technology that you convert to or choose for new builds today. For all of the processes, they look basically the same. You take water and you take salt and you make a brine. You adjust the pH and then you send it into an electrolytical cell. You will get hydrogen, you will get chlorine, and you will get your caustic solution, sodium hydroxide, which may need concentration. You take the depleted brine, you remove the chlorine, you adjust the pH to be slightly basic, and then you go into brine preparation again. So that's how you make chlorine, and that's the final inorganic chemical for you. And now turning to organic chemicals, we'll talk about steam cracking, which is basically pyrolysis in the presence of steam. So there's no need to add any oxygen. We just do a thermal breakdown of a petroleum derivative like naphtha or ethane or propane. And it's really a foundation of the petrochemical industry. It uses very high temperatures and it requires quite large energy inputs. We have a wide variety in feedstocks, from ethane to heavy naphtha, where ethane has become much more popular in later years due to the shale gas production of giving a lot of low-cost natural gas liquids. And you get a wide range of products, ranging all the way from hydrogen to fuel oil. And you add steam to make sure you limit the coke formation. You also have other additives, and interestingly enough, we add sulfur because the tubes that we use for the cracking, at these high temperatures, the nickel in the tubes will actually become catalytic for the carbon formation process, and by adding sulfur, you deactivate these catalytic sites. But even so, you have to stop every 40 to 100 days to decoke the process, which means that you add small amounts of oxygen and air at high temperature to get rid of any oxygen. And the steam content in the feedstock goes up the heavier your feedstock is. So processing ethane, you need less steam than processing heavier feedstocks. You also see quite a change in your your product mix. So if you put in ethane, of course, your ethylene production will be much higher than if you use propane, but for propane you get more propylene, and so on. And the process is quite fascinating. So we have naphtha coming in, going through a convective section to be preheated and vaporized. We add steam, then we go into the radiant section in the cracking oven, and the oven is of course fueled by some kind of fuel and air. And we then do the cracking reaction, and as soon as we leave the reactor, we want to quench the temperature as soon as we can, just to avoid secondary reactions like carbon formation in the transfer lines. So first there's a heat exchanger to extract heat, and then you add water to quench it. Then it's compressed, the acid gas and the water is removed. Again, we go in and we do a second compression step, and then we actually do what is called a gas drying. So we need to get all the water out, because the rest of this upgrading here is actually done cryogenically. So it's done at temperatures below 0 degrees centigrade, which means that any water would freeze. The first thing that happens is that we go into a demethanizer where we remove methane and hydrogen. Then we go into a second column where we separate ethane from the other hydrocarbons. And then we go into a third column separating propane from the other heavier hydrocarbons like C4 and pyrolysis gasoline. And the ethane fraction, it contains both ethane, ethylene, and acetylene. The acetylene is selectively hydrogenated, so we react acetylene with hydrogen to form ethylene, and then it goes into a column that splits the C2 components, and this is really a tall column. So it's about 60 theoretical plates, so more than 50 meters in height, but it's rather thin in diameter because of the low flow rates normally. And the height requirement is of course because you have such a close boiling point between ethylene and ethane. And the C2 splitter takes out the ethylene product, and the ethane is recycled to the cracker section. In propane, we do the same thing. We take the triple bonded C3 molecules and we hydrogenate it. We differentiate propylene, we send back propane, and in the bottom we get C4 components and pyrolysis gasoline, which can be used for other things. And yeah, another important part of the organic chemicals is aromatics. They're important for polymers, rubbers, and fine chemicals. They have a distinct odor. That's why they're called aromatics. But they also very common in biologically active components like paracetamol or estrogen, etc. They are hazardous because they're toxic, but they're also carcinogenic. And since they're so alike the human body communication system, they also disrupt the endocrine system. So, but aromatics is well used in solvents, in gasoline and other applications, but it is restricted. Ethylene is one of the major petrochemical products. It's produced at about 140, 150 million tons per year. We use it for making ethyl benzene and styrene for polystyrene, ethylene oxide and ethylene glycols, of course polyethylene, but also ethylene chloride to make vinyl chloride to make PVC. And it breaks down like this, that we do low density and high density polyethylene to about 50, 60%, then ethylene oxide, ethylene dichloride, and ethyl benzene. But the polymers and monomers really dominate what we make from ethylene. It's polyethylene, polyethylene terephthalate, polyvinyl chloride, and polystyrene that come out using ethylene. To make ethylene oxide, we use silver to do a direct oxidation in fixed bed reactors. It's quite similar to the production of formaldehyde. So we react it, we limit the reactant to just make the ethylene oxide, and we try to avoid the full combination reaction. So we limit the oxygen content and we use high recycling ratios for ethylene oxide. Polyethylene is about 80 million tons per year, probably higher now. It's divided in 4 shares. It's low density polyethylene for making plastic films for food and carry bags. It's low linear density polyethylene, plastic films, injection molding, etc. It's medium density polyethylene for pipes, and then it's high density polyethylene if you want to do blow molding like milk bottles, etc. And the crystallinity depends on the degree of branching, and the higher the branching, the lower the density, and that's because it interferes with the crystal formation. And the process, it's strongly exothermic. It works at low dilution, so it's a high concentrated process. It's using the product is very high in viscosity. It's like melt plastic, so you have to make sure you get the heat out. And there's actually a really important side reaction to consider, and that is the decomposition of ethane. And if you go above 300 degrees centigrades, you have to make sure that you avoid thermal runaway. It's done in either tank, tube, or fluidized bed reactors, and it depends on the quality to be produced. And you can see here that if you want to make low density polyethylene, so the one with high branching, you can do that in bulk plug flow reactor or CSTR type reactors. It's done in the liquid phase and it's using huge pressures. So we're talking 1500 to 3500 bar, which is really, really high pressure, the highest I know of in the chemical industry. It's much lower pressure for making high density and low linear density polyethylene. Polypropylene is processed very similar to polyethylene. So it's also exothermic reactions, 3 types of reactors. You use also the gas phase, bulk, or slurry phase type polymerization. Another important product from syngas is methanol. It's the reaction of carbon monoxide with hydrogen forming methanol, but it can also be from CO2 reacting with the hydrogen to form CO2, and these two reactions are again interconnected by the water-gas shift. The high pressure process was enabled with zinc chromium catalyst, but in the 60s, when there were better gas purification, we could start to use a new series of catalysts based on copper, which gave way for a lower pressure process. It's still not low pressure, but it's lower than the previous one. The classic process were here in the 200 to 300 bar range and higher temperature, and the modern processes are here in the 230 to 300 degrees C and between 50 and 100 bar. We have, again, syngas coming into a reactor system. We heat it up in multiple steps. We do reaction in multiple stages. We cool down in between to shift the equilibrium in our favor. We go into a separator, so we condense the methanol. We take the syngas back to the reactor. We have higher conversions in methanol synthesis than in ammonia. So here we end up with single pass conversions in the 70 to 90%, but we still want to utilize the syngas in a better way. We then go into a light end column where we separate out hydrogen, CO, CO2 that might be in the liquid here. And then we go into a methanol column where the methanol is purified. We actually get some higher alcohols that are ethanol, propanol, butanol, etc., that we can extract here, and we get the wastewater out here in the bottom. Methanol can be used also to produce a multiple of different things. Formaldehyde, acetic acid, methyl formates, other alcohols. etc. And it can also be reacted with aromatics to form terephthalate and methyl acrylate, which is the basis of the foundation for making plexiglass or synthetic glass. One of the major derivatives is formaldehyde, which is one of the major products for or outputs for methanol. About 40% of the world methanol is used for making formaldehyde. It's done either through dehydrogenation or partial oxidation, where the partial oxidation is the dominating one. There is two processes, one using silver and one using iron molybdenum vanadium catalyst. In the first case, we limit the conversion of methanol, and the other case, we use full methanol conversion. And the problem is that we have an explosion limit that we need to consider. The first process works on the lean side, the other on the rich side of this explosion limit. And it's very interesting because it lends itself to local production, which is different compared to most other chemicals. So you can actually set up multiple production sites rather close and still make money from it, rather than having one large centralized plant, because you need to transport the formaldehyde in a water solution. So logistically, it makes better sense to have it close to your production plant and move methanol instead. Final section, fine chemicals. They're characterized by high chemical complexity, so very complex molecules. They have low volume but high value markets. There's a few applications, so the more complex the molecule, the more specific it will be, so you can't use it for many things. And the product cycle is usually quite short. The bulk part of fine chemicals is drugs, so pharmaceuticals. The other large part is for agrochemicals, so pesticides and things like that. But then you also find it in food additives, fragrances, etc., dyes and pigments. They are produced in different ways. It can be chemical synthesis. It could also be biotechnology like fermentation and enzymatic catalysis, or they can indeed be extracted from plants or bacteria, or you can do protein hydrolysis for producing amino acids. Normally, it's produced in multi-purpose production plants, an MPP, where you have reactants and intermediates, but you have different reactors with different conditions, which you can combine with different separating units, and also do different post-treatments. They all can be combined in different ways for different products. So you have an individual reactor, you have a way of selecting different chemicals. So you add solvents, you add reagents, you add solids of different types. You control temperature, you control pressure, you do reflux. And then when it's done, you transfer it to the separation part, where you transfer it into a solid product perhaps and purify it. And then you have wastes handled as well. And you need to do all these things for different products with different feedstocks, which adds to the complexity. Finally, to conclude, this is a very large and a very diverse industry. There are several types of actors. They are not as well defined as they are in my presentation, and sometimes they fulfill many different roles. We divide the market into inorganic, organic, and fine chemicals or specialties. And the industries span all states of aggregation in the reactors and the production, and we see that catalysts are almost always present in the production. With that, I'd like to thank you very much for your attention, and I would like to wish you a nice day. Thank you. Bye-bye.